is called completing the square. Our goal is to create perfect squares and solve equations with perfect squares in them. So the first thing we want to do is look at what if you have a perfect square in your equation, how do you solve it? So if you look at equation A here, we would take our 3x squared plus 5 equals 20. We would subtract 5 from both sides. And what we're trying to do when we have a perfect square is we are trying to isolate the squared part by itself. So I'm really looking to isolate the x squared before I take the square root. So I divide both sides by 3 to get x squared equals 5. And then when I do take the square root, I need to remember that if I told you that a number squared turned out to be 25, you would think that the number was 5 or negative 5, because both of those numbers, if you squared them, would get 25. So this said x squared equaled 5. So when we say what x is or what the number is, we want to say it could equal either positive or negative 5. So in other words, every time you're taking the square root on both sides of an equation to get rid of that squared symbol, you don't know if it's positive or negative, and you should include both versions of your answer. So similar idea in part B, we would add 3 to both sides, so we'd get x squared equals 32. We would divide by 8, giving us x squared equals 4. We would take the square root, giving us x is equal to plus or minus 2. Okay, so that's 2 solutions for us. All right, we're going to skip example 2 and talk about that in class because it's more of an application problem. And then we're going to look at example 3. So example 3, all right, so when we look at this problem, we could try factoring, but we're not going to factor with a 9 on the other side because we'd want it set equal to 0, like we talked about today in class. But what we can do is I want you to recognize that in this problem, x squared plus 12x plus 36, if you do factor that, you get x plus 6 squared. Okay? So I guess technically we are solving by factoring, but this only works because instead of saying it's 2 things multiplying together to equal 9, it's 2 of the exact same things multiplying together to equal 9. So you have a much better option in this case. Okay? So the only time we want to solve by factoring when it's not set equal to 0 is if our factoring results in this perfect square. Okay? So what number squared would equal 9? You can see that by taking the square root or thinking about it logically, that number that's being squared needs to either be equal to positive or negative 3. And then to get x alone, we would subtract 6 and make sure you understand that there's 2 solutions happening here. There's a negative 6 being added or subtracted with 3. So negative 6 plus 3 would give us negative 3, and negative 6 minus 3 would give us negative 9. Giving us those 2 solutions. So this solving using square roots can be powerful if we have perfect squares in our equation. So the next thing we're going to focus on is making those perfect squares in our equation. Okay? And so we're going to look at this a little more in class tomorrow. But basically, if I have x squared plus 18x, and I'm supposed to come up with what constant right here at the end would be the best constant to have to make this a perfect square. Remember, this has to mean something squared would be multiplied to make that polynomial. 2 of the exact same things. With x at the beginning, we know it's x squared. We don't know the number at the end, or we would already know the constant. But keep in mind that that number at the end is contributing to your middle terms by making something x and something else of the exact same thing x. And together, they're supposed to make 18. Okay? So the only numbers I know that if they added together make 18 and they're the same number would be 9 and 9. So if I want 18x to be made in the middle, I need 9 and 9. All right, so I figure out that 9 should be at the end of each of my binomials. That doesn't mean that 9 is the number right here for c. It means c would be what I get when I multiply 9 times 9. In other words, my c would be 81. Okay, so I want this polynomial to be x squared plus 18x plus 81. But I don't want to have to go through this every time, so think about what we did. We took 18 and we basically split it in half because we tried to figure out what plus itself equals 18, and it had to be half of 18, which was 9. Okay, so we took 18, we split it in half, that gave us 9. But 9 wasn't the number at the end. It was 9 times itself that gave us the number at the end, so we squared it to get 81. So in general, we could say that you're taking the middle coefficient b, dividing it by 2, and squaring it. And that's kind of like a little mini formula you could use to figure out what number should complete the square at the end. So then using that idea, when we look at part B, when you see negative 9 in the middle, we would think about what is it divided by 2 and squared. And we'll just keep our answer in fraction form. This comes out to be 81 over 4. So it turns out that I would want my polynomial to be r squared minus 9r plus 81 over 4 would be my constant that I would want at the end. Okay. Now, part C is a little bit tricky because there's no way it's a perfect square with 2 as the coefficient of r. Okay? So what we would want to do is we'd want to think about factoring the 2 out, and that would leave r squared minus 9r. And let's think about the constant we want in there. Well, we already figured out what completes the square with 9 in the middle. Doing this math over in part B, we see that it's 81 over 4. So what I would really want here is 81 over 4. This is just like a repeat problem of what we just saw. But that problem didn't account for this 2 at the beginning. So if we multiply the 2 back in now, we would see the 2 can go with the r squared and the 9, giving us what we had previously. And that means the number that we want at the end for C in this portion is not 81 over 4, but it's actually 2 times 81 over 4, which would be 81 over 2. All right. So we're going to actually use this process now to solve equations. So rather than by factoring, we're going to solve them by this method called completing the square. So to do so, we like our first and second terms of our quadratic, but we're looking for a perfect square that goes with those to be the third term. So I'm actually going to move the 120 to the other side of the equation because it is not the perfect square that I'm looking for. Then we're going to figure out what the perfect square would be, and again, we can take that middle term, divide it by 2, and square it, which in this case, that will give us 1. If you did this correctly, then what you have on the left side of this equation should factor as a perfect square. And in this case, it does. It factors as x minus 1 squared. Now, I did forget one very important thing about my right side. I can't just add 1 to the left side of the equation and have changed it and still say it's equal to 120. I would also have to add 1 to the right side of the equation. So this is actually going to be equal to 121. Now I'm going to go ahead, take the square roots of both sides, and this is going to give me x minus 1 equals plus or minus 11, giving me that x is equal to 1 plus or minus 11. So my two solutions are negative 10 and positive 12. And you could plug those back in and check and make sure that they work. So again, looking at part B, we want to do the same thing, but again, B has that 2 looming out there. So first thing is, 12 is not the number that I want for my constant. I already know that. So the first thing I'm going to do is just separate 12 to the other side by subtracting 12 from both sides. I want a constant here that completes the square, but I can't really do that with that 2 sitting here. So I'm going to factor the 2 out. So I've done that. And now I'm going to complete the square inside of the parentheses. This is like we did in part C of the previous problem. So remember how I do this. I'm going to take that middle term, even though it's a fraction and it looks all scary. I'm going to take the negative 7 over 2, divide it by 2, and square it. And if you mess up your fraction operations, my advice would be write it out like you used to. Okay, you learned this. You got good at it. So you have negative 7 over 2 divided by 2, which is really negative 7 over 2 times 1 over 2, which is negative 7 over 4. And that's being squared. Okay? That's what I want my constant to be. So my constant is going to be 49 over 16. Okay? Now remember, when I add something to the left side, I need to add to the right side. And it appears in blue here that I added 49 over 16. But don't forget that that 49 over 16 is in parentheses, and attached to that parentheses is a times 2. So when I go to add that 49 over 16 to the other side to keep equal amounts, I cannot forget that that 49 over 16 was being multiplied by 2, so that I've really added the exact same amount. Okay? Now, if I've done this correctly, what's inside my parentheses should factor as a perfect square. Okay? And 49 over 16 is a perfect square using 7 over 4. It'd be negative because the middle term is negative. And x would be at the beginning. Oops. So we have an x at the beginning. We have minus 7 over 4 squared. And then over here at the end, I have my negative 12 plus this 49 over 16 times 2. That's like 49 over 8. I'm going to make a common denominator to add them together. So this is like negative 96 plus positive 49, which is going to be negative negative 96 plus positive 49 is going to be negative 47 over 8. I already wrote the negative, so I don't need that. Then the next thing we would do is divide by 2. Okay. And we would get x minus 7 over 4 squared equals negative 47 over 16. Now, if you're wondering how I got that 16, write out this negative 47 over 8 divided by 2, just like I did over here on this side, with 7 over 2 divided by 2. And then I'd want to square root each side. Now, at this point in our problem, we have a negative underneath the radical, so for us, we're going to say that this has no real solutions. But we're going to come back to this problem at a later date and learn that just because it has no real solution doesn't mean we couldn't finish solving it a different way. Okay? If it did have real solutions, we would keep solving it the way that we normally do. Okay, the next thing we're going to talk about is writing each equation in vertex form. So first of all, I just want to remind you guys that vertex form for our quadratics looks like a times x minus h squared plus k. So we want to make the equation look like that, even though, as you can see, these equations are in standard form. So for this first equation, y equals x squared plus 10x plus 27. 27 is not a perfect square and definitely not the perfect square that would go with this middle term of 10. I want to put my own constant in this equation to make it factor like a perfect square. So I'm going to put x squared plus 10x, plus I'd like to add on my own. I'm trying to make a nice little perfect square here. Okay? But I can't just remove the 27 from the problem, so it's still there, and I acknowledge that. I'm just kind of moving it outside my parentheses so I can focus on making this area a perfect square. So with a 10 as the middle term, remember we would take 10, divide it by 2, and square it to determine what we want to add to each side of the polynomial, okay, or to determine what number completes the square. So we have our 10x. 10 divided by 2 is 5, squared is 25. Okay, so everything here was here before, but I added 25. Now remember, I can't just add what I want to some side of the equation. I've changed the problem completely. So I either need to also add the same amount to the other side, or I could subtract the same amount on this side. So it'd be like if I gave you $5 and then took $5 away on the same side of the equation, you would still end up with 0 extra. So what I'm going to do is outside the parentheses over here, because I added 25, I'm going to subtract 25. That way, I have really added nothing to the equation as far as quantity. However, our equation looks different, and it looks like we have a perfect square now. So now what this is going to allow me to do, and remember, if we did completing the square right, we can factor this. Okay, so if we did this right, we're going to get this perfect square. And so if I factor this, I do get x plus 5 squared. So that gives me confidence I chose this number correctly, the 25. But then I had to make sure I balanced it out, which is where my minus 25 was. And then these two constants can combine together to just equal plus 2. And now we can see that same quadratic, and instead of in standard form, it's now been written in vertex form. Okay? And you don't have to translate everything to vertex form. But this is a skill that we can use here, and we can also use some other places, so it's important to know. Now, in part B, it's going to be a little bit trickier immediately because of the 2 coefficient that's in front. So the 2 is going to cause us a little problem, but we'll work through it. So first of all, 10 is not the number that is a perfect square, going to complete my perfect square. So I want to think of 10 as kind of being separate from where I do want to complete the square. And out of these 2 that I'm going to include in that polynomial, I know that having the coefficient of 2 there, I can't do while I'm completing the square. So I'm going to factor the 2 out of this. Now, I'm not factoring the 2 out of the 10, and that's okay, because in my equation, I didn't do anything illegal. The 2's out here, and notice the 10 is outside of the parentheses. So I'm not saying I factored a 2 out of 10, and that's why the 10 doesn't have to change. Okay? Now, again, we're going to do what we did before. To figure out what we want to complete this square, we're going to take the middle term, which is 7 over 2. We're going to divide it by 2, and we're going to square it. So if you have to go back to the previous example about how we did 7 over 2 divided by 2, that gives us 7 over 4. And if we square that, we're going to get 49 over 16. So 49 over 16 is the amount that I'm going to add right here. Now remember, it looks like I've added 49 over 16. That's what it says in blue right here. But that's not the true amount that I've added to my equation. I've really added 49 over 16 times 2. So just like in this last example, when we added 25, we had to subtract 25. We have added 49 over 16 times 2, so we need to subtract 49 over 16 times 2 also, okay, to make the equation balanced so we haven't actually changed the value. So again, if I've done this right, I have my factor of 2, and this should factor as a perfect square, and then I need to do some arithmetic to combine those like terms. So x would be at the beginning. It would be plus because this middle term is positive this term, and 49 over 16, 7 over 4 is its square root, so that should factor well. And then over here, I have to add 10 with this problem here, and 2 goes into 16 8 times, so it looks like 49 over 8. And if I want to make 10 over 8, so it's like it's over 1, I multiply by 8 in the denominator to get 8. Then I also need to multiply by 8 in the numerator, which is going to become 80. So then what I'm going to have here is an 8 in the denominator, and 80 minus 49 is 31. So it might not look pretty. There's fractions and all of this, but it's fine. My equation is y equals 2x plus 7 over 4 squared plus 31 over 8, and now I have the equation in vertex form. All right, so that's all for today's lesson. Just make sure you copy down those notes, and we will talk more about it in class. Thank you.